Okay, well, the gentleman in the hallway said that I could start. So I'm here today to tell you a bit about OpenStack networking and routing on a host, a new concept that, well, marketing launched. It's not really new, but I'm going to tell you what we're doing with it and how it can integrate with OpenStack. Now, not everyone knows Cumulus networks, so I do have to intro a bit what we're doing and who we are. So we have developed a network operating system, and that runs on white box and branded box switches. And that's different than what you're used to while you're buying a switch with an operating system, say a Juniper or an Arista that comes with their OS, and you're limited with the operating system that you buy from them. Now, our idea, or the open networking idea, is that you buy your hardware, whichever vendor you want to. You run an operating system, preferably Cumulus Linux, of course, and then you are able to integrate it with the applications that you're already using. Now, you might be thinking hardware-wise, okay, what am I buying? Am I buying some cheap Chinese things? How does that work? Now, it's not really different than what you're used to. So the hardware is based on the same hardware that you've been using for the past few years. If you're looking at Juniper hardware, Cisco, Arista, they are all based on the same chipsets for hardware forwarding, mostly Broadcom over the past few years. And it's derived by a PPC CPU or x86, and you can just install an OS on that. Now, that's the same thing in white boxes or bright boxes. So white boxes is usually what the vendors are, well, they're subsidiaries. For example, you have only 6 vendors in the world that actually make the hardware, and EdgeCore is, for example, one of them. On the other hand, you have the bright boxes, which are Dell, HP, and Mellanox for us, and we are supported on their hardware as well. Now, there's one different thing. Most of the hardware was based on Broadcom chipsets over the years, and Mellanox has developed a new chipset, the Spectrum chipset, that has several advantages, but I'm not going to tell you about that. You have to go to the guys here at their stand. Now, how does that look from an OS perspective? Our operating system is based on Debian Chassis. It's basically the same. There are a few additions made, and the most important one is a switching daemon. So the switching daemon that we have looks at the Linux kernel, and all the basic networking things that you have in the Linux kernel are read out and programmed in hardware. So that means that whatever is in the Linux kernel, that's the single source of truth for us. And not with the classical vendor where you have maybe a Linux kernel running or Juniper a BSD kernel, and on top of that is an application that does everything for you. Now, basic switching is done using all the standard Linux tools that you already know, so bridging, and you can control it with BRCTL, for example. We've made some additions, so we have a bridge that is VLAN aware, instead of that you need to configure a bridge for every VLAN that you have. And most recently also a bridge that has VXLAN support. So you only have one bridge. You could theoretically configure multiple ones, but for administrative reasons I wouldn't recommend that. Now, for all the routing that you have, we use Quagga. We develop heavy on that, so it's also different than what's upstreamed right now. Simply because not all patches are accepted upstream, but you can download our version as well if you want. If you're not satisfied about our routing daemon, you can also run something else. For example, Bird, or I heard that there's also a BGP daemon written in Go. If that's your thing, then you are able to run it. It does have support consequences, but yeah, that's a different story. Now, for all the overlay technologies, we have OVSDB running on the switch itself, so it can integrate with NSX and several other overlay technologies. I'm not going to dive into that because there are different solutions for in that, and they all work differently, and I don't know all the specifications. One important thing for us is automation. So since we're a standard Linux environment, you can automate it with the Linux tools that are already out there. So if you're using Puppet, you can simply use Puppet or Ansible. Now, you might say that some of the vendors already have that. That's true. However, you're depending on the modules that they provide you. and they might be limited, might not support all the functionalities that you have. But also the thing is that if the entire community decides tomorrow that we need a new automation tool, then they won't be able to keep up, and we will, because you can just use templates and such. Now the last thing is monitoring. What we see from most system administrators is that they don't handle a switch anymore as a switch. They see it as a server which happens to have 48 ports. And you can also use monitoring that way. So you can install a client that you already used to, like your Nagios client, but also other tools like Telegraph or CollectD to send it to a time series database, which should be more scalable. Now, one thing is that we don't want to just make an OS and ship it or sell it and say have fun. We're quite involved in the open source community. For example, VRF support. Linux didn't have any VRF support over the past few years. There were a few attempts with namespaces, but that wasn't really accepted in the kernel. Now VRF support is in the kernel now since 4.4, and that was made by Cumulus Networks, and there will be several more patches for that. But also something like ONI, which is the bootloader for white box switches, that was developed by Cumulus and used by everyone these days. Now one important thing is that we would like to be involved in the architecture of a network. So you can still have an old architecture based on MLAG, but most networks are not anymore, and I'll explain why later. But MLAG is a familiar technology for most people. It combines two switches and it has a single control plane for the attaching host or switch. It looks like one device and it balances traffic over it. Now you still have your VLANs, and you can take your VLANs over it, and you have your connectivity, and you can also do your tenant separation. Now if you combine that with OpenStack, you get something like this. You have your two tenants, they have bridges assigned to them, and you assign VLANs to them, and you tag them over your network, so you separate your tenants. Now usually you have a router on a stick model, or some core that you connect to. And you can also do firewalling, etc. That's how you would do that. Now the problem is that an MLAG topology isn't very scalable. What we've seen in data centers is that you see way more east-west traffic than traffic from servers to clients. And the problem how you can solve that is by adding more spines. With MLAG you can't, because you're limited to two switches. The other thing is, if you have two switches and one breaks down, you lose half of your bandwidth. So that's also a thing why you would like to have more than two. Now, if you would set up a routed backbone, so you use BGP or OSPF on your backbone, you can balance traffic using ECMP. So you have multiple routes to a destination, and you can then balance traffic over that. Now this is an example of a typical pod. There are 6 spines because a typical Trident 2 switch has 6 uplinks, and then you have a 1 and 2 oversubscription. Now leaf switches can be 10G or 25G these days. 25G is a new IEEE standard. Only Mellanox has a box that you can actually buy that has 25 gig natively these days, but you will soon see it in other vendors as well. For the backbone links, you either use 40 gig or 100 gig, but we see a lot of customers going directly to 100 gig because the prices are very close by, and you don't want to invest in a technology that's going to disappear anyway. Now, how would that look like from a routing perspective, and how would you define that in your network? The thing is that a lot of people are used to layer 2, so they still want that layer 2 connectivity between the racks. They still want their tenant separation in OpenStack, for example, using layer 2, or different other reasons. So what you usually do with that is you have tunnels being built between the leaf switches. You can use VXLAN for that. VXLAN has become the default tunneling protocol to arrange that in networks these days. Now, for you who are familiar with VXLAN, you know that's not really different than you are used to. It's the same tunneling protocol or tunneling mechanism that we have for the past decade or so with GRE. It makes a difference using looking at the control plane, and we'll get back to that in a bit. Now the thing is, how would that look like for an OpenStack environment? Because you will still have your VLANs on your host, and you will still want to use that for tenant separation, but your compute nodes want to reach the other compute nodes where also a tenant can reside over your backbone. Now that is something that we call hierarchical port binding. And basically what you do is you map a certain VLAN for a tenant to a VXLAN on your backbone, which arranges you the connectivity that you already wanted. Now this you can all do this using ML2 plugins, and it should be quite easy to arrange. If you want to see a demonstration, you can look it up. One of my colleagues has presented that at an OSS. I don't know which one exactly, but it was a while ago, and well, you can easily provide the tunnels that you need for your network connectivity. Now, what are the reasons why you would want this? One major advantage is that the VXLAN encapsulation and decapsulation is done on your leaf switches. It is done in hardware. It can be done in the Trident 2 chipset or the Mellanox chipset in hardware as well. So you don't need anything on your hosts to actually do that line rate. So you can use them to do the encapsulation and decapsulation. And then you can still have 10 gig or whatever traffic you need for your tenants. If you look at a traffic flow, how that then would look at your network. So you have a compute node which has the ML2 driver as well that you can speak to. The leaf switches that build the tunnel, and usually you have a separated network node where you first send your traffic before it goes to the outside world. Now that depends a bit on the overlay technology that you're using, but this is how it would look like. Now, we want to take it a step further. What we would like to do is extend your IP fabric all the way to the host, and that's the new concept that we have. We call it routing on a host, but it's not really new. It was done in IPX 20 years ago, but simply everyone got addicted to layer 2. But now we're back here. So what you do is you install Quagga, that's our routing daemon. You install it on a host, and you set up BGP sessions, that's the default protocol in data centers these days, to your leaf switches. And you announce your loopback address. That means that you have full connectivity between the compute nodes again. Now, that also means that you don't need MLAG to your leaf switches anymore, and that's a good idea because MLAG, you still have that control plane between leaf switches. And of course we test everything, and from a customer side everything is tested as well, but you still have that control plane that you rather not have. Since you have the 2 BGP sessions, or 3, 4, because you're not limited to 2 top-of-rack switches, you can balance your traffic over your links to your leaf switches. Now, you can use our Quagga if you want to. Several customers have asked for that because they were aware of the concept, and they said, we want to use your Quagga version on that, but we need someone to call if it breaks down. Now, we have some customers that like the concept, but they want to use Bird. Sure, Bird can use BGP as well, and you can set up your sessions too. Now, how would that look like in an OpenStack environment? Simply every compute node has an IP address, and you set up VXLAN tunnels between the hosts. Every tenant has a bridge, and that means that that bridge has connected a single VXLAN, and you have your layer 2 connectivity again. Now, if you look at the traffic flow then, you have the same picture, but then the VXLANs are between the hosts. And that means that you move all the intelligence to your hosts instead of that you're solving it on your leaf switches, and that you have to map VLANs and VXLAN IDs as well. There is an issue with bandwidth, of course, and that's the VLAN encapsulation and decapsulation. Now, if you look at the most recent NICs from Mellanox and Intel, and there's another vendor, they can do VXLAN encapsulation offloading on the NICs. So if you use them, you can still have the same I/O throughput with 10, 25, or 100 gig, and then you solve that issue as well. Now you might say, is the configuration not very hard? Well, I personally think that it's not much harder than configuring bonds and configuring LACP. So this is a example of a configuration using Vagrant. Now if you look on the left, that is how you would, in a classical situation, configure BGP to two different top-of-rack switches. So you have to configure your interface addresses, both IPv4 and IPv6, of course. You have to configure your AS number, router ID, and your neighbors. Now the thing is that we have made several additions that should make your life easier in this. One is that we use BGP unnumbered. So you can see on the right that you don't have to define your interlink addresses anymore. Now, unnumbered addressing, as you are not used to in WAN interfaces, for someone who has done a certification, you might have come across that, or a very old network. That's not really possible on Ethernet interfaces. So what we did is, as soon as you enable an interface, you configure an IPv6 link local address is added. Using those v6 link local addresses, we established a BGP session with your neighbor. You do need to know who your neighbor is, so we use IPv6 router advertisements for that. And if you know your neighbor, then you can set everything up. Now, one addition is, for example, the router ID. So you can get that from a loopback interface, since that's already there. And the neighbor AS numbers. In data centers, by default, it's eBGP is used. And with eBGP, you have to have different AS numbers. Now, it doesn't really matter who your neighbor is, just the fact that it is a different AS number. And, well, then we have just defined it as an external. Now, because you need not as much variables to configure, that makes automation much easier as well. So I have a full configuration example here, how it would look like from the switches. And you see that it's just 20 lines. Obviously, BGP has a lot more knobs that you can use, but this is enough to get it working. Now, one thing that we have, because we're a standard Linux environment, is that we have a virtual machine available. And you, well, you can freely download that from our website in VMware, KVM, or VirtualBox. Now, what we also did is we made it available for Vagrant. So you can also incorporate it in a Vagrant file, and you can distribute that to customers or partners or for yourself, and you can demo with it. Now, we had a lot of customers that have been using that, and we actually made it part of our product, which means that it is an exact copy of the Linux running on top of our switches without the switching daemon, because it has no hardware to be programmed. And that has caused customers to really use it in development and everything in their environment. So one thing that you can do is, for example, adjust counters and do the readouts as well. Now this really helps if you're in DevOpsing your entire network. So for your provisioning to provision everything, but also changes afterwards. We have a few customers that spin up an entire virtual network, and before doing a production change, they first do that in a virtual environment with GitLabs or something, and then they will move it to production if all the checks are good. Now, what you can download from our website is also a full topology. You can just download the Vagrant file, and you can spin up the entire topology, and then you can roll out any configuration that you like. It can be a classical MLAG, but also routing on a host like I'm going to show you. but also with, yeah, always with live demonstrations, it's a question if it's going to work or not. So I did cheat a bit. I spinned up the virtual environment just before getting in here. It takes 15 minutes, so that's one of the reasons. But I wanted to show that it's really brand new and just running. And what I did, I downloaded one of our routing on a host demos in Ansible. And I want to, well, just roll it out and show you what the results are. Now, what you can see here is that it will edit two files, mostly. If you look at the Cumulus Linux configuration, if it works, hopefully. Yeah, it does work. If you look at Cumulus Linux, since it's a Debian derivative, all the network interfaces configuration is in the file etc network interfaces. So you only have to adjust the settings there. All the routing settings for Quagga, they're in a routing or in a Quagga configuration file, and you can edit that as well and do your reload to make everything working. Now, we don't really have a CLI right now. We have one in early access because what we didn't want to do is have an OS with another CLI that would limit you in what you were able to do with the system. What we now made is a CLI, but that will actually edit the configuration files for you, and you will see what that CLI does for you. So you could compare it a bit with the commit feature that Juniper has, but that won't be editing a configuration file. So what we do, we add a local Git repository, and you will be adding configuration statements using a net command. And you will be able to do tab completion. You will be able to get examples on if you want to configure OSPF, for example. It will show failures. So if you type in the wrong command, it will show you examples on what you might have meant for that command. So that's quite easy. Now, one thing that I can show you for how that would look like in Ansible. Now, I have a standard Ansible setup with different roles. So if I look in the roles directory, I have a few roles because we're also configuring the hosts itself with a Quagga daemon. And since the hosts itself are just Ubuntu hosts, we have to deal with IF updown 1. And as you know, IF updown 1 has quite some bugs. It might not always work. You sometimes have to even reboot the host. So that is one of the reasons that Cumulus developed IF updown 2, which is also upstreamed, and you could install it on the latest Ubuntu as well. Now, and these roles, if I, for example, go to the Quagga directory, this holds a template that will configure your Quagga configuration. Now, I'm not sure if you're familiar with Jinja templates, but basically what you're doing here, and most people, even if you're not familiar with Ansible or Jinja, will understand what I'm doing here. So this is the part that will configure BGP, and you see that it's a standard configuration, and it will just fill in the blanks by the variables that you've set in one file. And that single file that I'll show you later, that is something that you would add. You wouldn't change these templates anymore. And that makes your environment much more stable when you're doing changes. The thing is that you predefine all your configuration that you have, and only when you have major changes, then you should adjust your code. And that helps a lot for the stability. Now, let me have a look at the variable file. Now, that is what I just said about the number of variables that is needed to actually configure a host. As you can see, for one host we have 6 variables that you need to fill in. As I said, you can use a lot of more knobs, but this is enough to make a working configuration. And for a lot of people, having so less or this number of variables to edit, that's great to handle. You could even hand this out to your help desk, and they can add a host very easily because, well, this is something that they can understand. If you use something like Ansible Tower, this is something that you can integrate quite clearly too. Now let me see how far the provisioning has come right now. Yeah. So what I'm going to do, I'm going to log into one of the leaf switches of the topology that you just saw. So where I was running the Ansible script is from the out-of-band management server. So in this reference topology, you manage everything from an out-of-band management server like you would do in a real network. You can call that your controller if you want to in SDN terms, but you can configure everything from there. Now, I'm logged into the leaf switch. As you can see, it's just a normal bash prompt, and that is how you would get your normal switch as well. And I've just configured all the routing, and I'll show you the configuration for that, but you can see that it already has multiple routes to different destinations. Say that I have a look at the interfaces configuration. Then you'll see that I have this standard configuration, and it's not a lot, because the only thing that I need is the loopback address. I have an Ethernet interface for out-of-band management, and I have 4 interfaces, 2 to my spines and 2 to the hosts, where also BGP unnumbered is running. So this is the only thing that I need, and something that I can also clone to other new hosts. Now say that I go to the shell for Vagrant. Then I can see that you can see that there are 4 switches up and or 4 BGP sessions up and running. 2 to the spines and 2 to the servers. Now, what is important here is that you see the names of the switches and the servers, because you usually don't know. You only know a neighbor IP address, and in this case, our neighbor is defined by the switchboard. Now, there's a new RFC draft that we've used for that, and you can announce your host name over your BGP session and use that to display that here. And if I now look at my routing table, you see that, for example, 10.0.0.12, that it has 4 different destinations, and it will do ECMP over those routes. Now, let me log into one of the servers that I've also added. Now this also has Quagga installed, so I can also go into there and show you an IP route. For this, you also see that that it has multiple routes. It has BGP sessions, and it can reach everything. Well, I can test that, of course. But yeah, that is how it works. Now,
sorry, is that a virtual machine we're looking at?
Yeah, this is a virtual machine.
So you're running BGP on every virtual machine in the data center?
Exactly. But since it's just Linux, but it doesn't program anything in hardware, it would act the same as it would on real hardware. Obviously, no ASIC issues or anything with the SDK. That's a different story. But you get most of the customers can test everything they do or changes in on the VX as well. Now, one thing that I want to show you is if I add a new switch. Now I currently just have 2 leaf switches, but what if I add more? I already cheated by adding them to the variable files, so I can easily add them. Now, as you can see, I added 2 leaf switches and 2 servers that are connected to it. And you can see them on the right side that are leaf 3 and 4 and the 2 servers that are connected. And the only thing that I have to do is now run the playbook again. And they should be configured at the end. Basically, this is what I had as a presentation in mind. I'll let this running so we can see it at the end. One thing that I do like to mention, as you said, this is a virtual environment, and one thing that we wanted to show at the last OSS in Austin is that it's not just a lab environment, that it really works in a real situation. So what we did together with Red Hat and Dell, we reserved 300 servers in their environment. And with Red Hat we deployed a complete OpenStack configuration over their lab situation and with real servers. Now the network was up in 15 minutes, and it was all done remotely using Git repositories and Ansible. And the complete network with OpenStack was up in 6 hours, and everything was functioning and ready to be used. Now, that was what I had in mind. Are there any questions?
Do you see, you might, I don't know whether you might be able to talk about this or not, but do you see many hardware products come out using Intel's DPDK? Is that something that you're looking into integrating with? Because I know that can provide some of the hardware performance sort of for LASIK, but on a more general purpose x86.
Yeah. So, well, that will be more for general hosts, and currently we're focusing on the switching side. We know that it's out there, but I don't know how it's involved or how are we going to be involved in that. But it's an interesting market, especially for service providers, because what you could do is have an x86 server with 4 NICs, all 100 gig, and you can offload everything. Yeah. That would be replace a very expensive Juniper MX, for example.
I have to say that's what we're doing at Brocade.
Sorry?
A little plug, that's what we're doing at Brocade. That's what we ship, basically.
Yeah.
I should also say, Monologue's got DPDK on the
Oh,
people getting into blatant books.
I don't know these guys, by the way.
Yeah, no.
I've seen this routine.
So I think I missed a bit about the way the peering gets set up between, say, the server, when you added those 2 servers,
yeah.
You added the server at the end of the fast switch. Yeah, how did that peering get set up? How did it know where to peer with?
So let me see. It's done now, but I'll show you in a bit the configuration. So server 04 has 2 BGP sessions, to leaf 03 and leaf 04. But it has BGP unnumbered links, and it knows the neighbor between because of the router advertisements that are being sent back and forth. Does that answer your question? So I can show you that.
It was where are we right now? Sorry, we're on.
So I'm logging into server 04 now.
Okay.
And say that I look at ETH1, you see that it only has the IPv6 link local address.
Mm-hmm.
So you see that right here you see that here the remote host is also a link local address, and it's from one of the leaf switches. Now there's one thing that you do have to configure specifically, and that's the RA interval. Because by default, router advertisements are being sent every 10 minutes. And that's not really a good thing if you want to set up a BGP session and you have to wait 10 minutes. So we decreased that to 3 seconds. But since it's only local on that link, that should be no problem.
Okay, so that's how you peer to the leaf switches.
Yeah.
And then you learn about, because you're also configuring the remote server, the other side of the server,
Yeah.
so you're getting that through the advertisements from the
Spine switches. Yeah, so if I So, for example, you have another server, that's server 1, 10.0.0.11. If I do a trace route, I hope that's installed. So you can see that it goes to the leaf switch and then over the spine back to the other leaf and then the host.
Is there a way of automating the assignment of the AS numbers?
Well, what we see people do, that they don't really care about the AS number, so they have just a pool and they assign that to servers or leaves. Sometimes they care about it in the sense that you want to have it per pod, and you can randomize that too if you want to. So that does cause problems if you have a very big network. Then they use ASN32 addresses for that. But yeah, there are several ways. But it depends on how you would integrate it with editing that variable file and how you would assign it to your switches. Okay, well, thank you for the attention. If you have any more questions, we have a booth there and I'll be walking around for a bit. I do have to run because I have to give the same presentation at Openstack Benelux tomorrow and I have my plane that I have to catch tonight. Thank you.